Hello and welcome to part 2 of the video series in which we are discussing singular value decomposition. In the previous part of this video series, we discussed eigenspaces and positive semi-definite matrices, and the purpose for discussion on eigenvalues and eigenspaces and positive semi-definite matrices is to actually get a good ground for derivation of singular value decomposition. So in this particular video, part 2, in this part of the video, we are going to derive singular value decomposition from scratch. So we will write all kind of details to derive singular value decomposition, and we will be using eigenvalues and positive semi-definite matrices, the properties of positive semi-definite matrices to derive SVD. So also in the next part of this video, we will be actually implementing singular value decomposition from scratch in NumPy. So let's start the derivation of singular value decomposition. Okay, this is probably the most fundamental concept in linear algebra, as well as in most of the linear solutions in data science. Singular value decompositions or also sometimes called SVD, a very powerful solution, and it gives very fast implementation of principal component analysis as well. Anyways, here we will be discussing singular value decomposition completely independently from principal component analysis, because we have a full module on feature extraction. We will be discussing and linking all these concepts together, but right now I'm going to discuss this completely independently. So as in the last video I mentioned, a matrix is called orthogonal if it is a square matrix and all its columns are orthonormal. Such a matrix is called orthogonal matrix. Or an equivalent definition is if a matrix has inverse as its transpose, then the matrix is called orthogonal. So for example, if you have matrix A and you multiply A with the A transpose and you get identity matrix, and the same goes if you multiply A transpose with A and you also get identity matrix, then A is called orthogonal matrix. And one property of orthogonal matrix is all its columns as well as all its rows, they are pairwise orthonormal. Yeah, so that is, but this matrix is not called orthonormal. Mathematically, this matrix is called orthogonal rather than orthonormal. Maybe orthonormal is a better name, but if you search for orthogonal matrix, this is what it will pop up. Singular value decomposition. The idea is the following. Given any matrix A, maybe a square matrix or maybe a non-square matrix, maybe a rectangular matrix, any matrix A, given a matrix A, can you decompose a matrix in the following form, where you have U as some matrix, you have S, or sometimes written as D or S, and this V transpose. Can you decompose your matrix in a following form where both U and V, they are orthogonal, and this D is diagonal? So the question is, can you decompose a matrix? Can you come up with three matrices such that the first matrix is orthogonal, it's a square matrix with the transpose as inverse, and the last matrix, which is written as V transpose, it is also a square matrix and orthogonal matrix, which means its inverse is its transpose, and the middle matrix is the diagonal matrix, is some diagonal matrix. Can you decompose any matrix in this form? Because if you can do, there's a lot of applications that you can do. But the first question is, can you do that? And this particular decomposition, if you can do, is called singular value decomposition. And the good news is we can do this for all matrices, all real matrices, no problem. So here I'm going to actually spend some time on SVD, just a proof of it, just for those who are curious. Think about matrix A, which is UDV, and multiply this matrix A with A transpose. So you will get UDV transpose, which is A, and then transpose of A, which is UDV transpose transpose. this. Okay, now transpose of a product A, B transpose, as I mentioned earlier as well, that is equal to B transpose A transpose. So if I multiply this, if I apply this transpose on this product, the order will reverse, and this A transpose, this will become UD V transpose, V transpose transpose, D transpose, and U transpose. Yeah, so this V transpose transpose, that simply becomes V, that is V, because transpose of A and then transposing again gives the same matrix back, so that is V. And V transpose V, that becomes identity because they are inverses of each other. Remember, this V is orthogonal matrix. So this A transpose, this becomes U, D, identity, D transpose, U transpose. Now this identity goes away, and D is a diagonal matrix, so transpose of a diagonal matrix is itself. So this becomes U, D square, U transpose, A transpose. Here you can see U is orthogonal matrix, this is transpose of the same matrix U, and this is a diagonal matrix. D square is a diagonal matrix. Further, notice that this A transpose, that's a positive semi-definite matrix. As I told you earlier, every matrix of this form is a positive semi-definite matrix. Yeah. So now, because A transpose is positive semi-definite, and we want these matrices such that A transpose becomes this, we can find out this U and D square very quickly. What do you think? Can you see this last equation? If S is positive semi-definite, then this matrix is just the eigenvectors of S, and these are eigenvalues of S. So from here we can see U is matrix of eigenvectors of A transpose, and D square is matrix of eigenvalues of A transpose. So we have found U, we have found D square at least. Once we have D square, we can find D just taking the square roots of the eigenvalues. And we can take square roots because A transpose is positive semi-definite. All its eigenvalues are non-negative. So D square, the entries of D square, all are non-negative. So we can safely take square roots. So we can find out D by just computing the eigenvalues of A transpose and then just computing the square roots. Now the only thing left is V. How can we find out V? The same trick goes for V. So remember now, finding out U is straightforward. Multiply A with the A transpose and compute eigenvectors. U is there. Set of all the eigenvectors. And the eigenvalues, compute their square roots. We have our D available. Now we need to find out V transpose to complete the singular value decomposition. Now the trick is first we multiply A with A transpose. Next we multiply A transpose with A. And if we multiply A transpose with A, we'll get UD V transpose times UD V transpose. And according to the same argument, this will give us V D transpose, U transpose, UD and V transpose. This becomes identity, D transpose and D, their diagonal matrix becomes D square, and we have V D square V transpose, A transpose A. Again, A transpose A is also a positive semi-definite matrix. Maybe a different matrix, they may not be same. A transpose and A transpose A may not be same, they may be different. But see one common thing. A transpose and A transpose A both have same eigenvalues. The eigenvalues of A transpose is the same as the eigenvalues of A transpose A. Although the eigenvectors, they are different, but they also have a certain relationship. Anyways, so to find out this V, we just compute the eigenvectors of A transpose A is eigenvectors of A transpose A, place them in a vector, place them in a matrix, place them as columns of V. So V is a matrix of eigenvectors of A transpose A. And once now we have U, we have D, we have V, no problem. And that is called singular value decomposition. So if I write the algorithm is really simple. Compute the eigenvalues of A transpose, eigenvalues and eigenvectors. Compute the eigenvalues and eigenvectors of A transpose A. And then you have your U, you have your D, you have your V. And this particular decomposition is called singular value decomposition. And it is extremely popular, very simple to explain, and very simple to understand what is happening inside. And it's extremely powerful in so many areas in data science. Apart from its use in optimization theory, it has a lot of properties. It has a lot of information about the matrix for which we have just calculated the singular value decomposition. The singular value decomposition is one of the most popular factorization of a matrix, and it has a lot of information about the matrix. For example, let me show you. Let's say we have some matrix A. Let me show you that matrix A. This matrix A need not to be square matrix. It may be a rectangular matrix. It can have any shape. So let's say this is a matrix A, and we have its singular value decomposition. Let's say U, matrix U, and then we have this D, and then we have this V transpose. So what is the information? So if we have, for example, singular value decomposition of matrix A, what information about A do we have? For example, if there are a lot of properties of matrix A, we are going to explore a lot of these properties using the singular value decomposition. So if we have, for example, if we have done singular value, we know how to do singular value decomposition. That's the procedure. If, for example, we want to know that once we have done singular value decomposition, can this singular value decomposition SVD explain some of the properties of matrix A? So here I'm going to explain those. For simplicity, I'm just thinking that this matrix U consists of columns U1, U2, let's say this matrix is D by N. So this matrix U can be D by D. This matrix D can be D by N, and then this matrix V transpose can be N by N. So this U1, U2, dot 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 UD, these are all the columns of U. So let's say these are columns. So these are columns here. The matrix D contains certain values. Let's say S1, S2, dot 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 D values. So D values. Obviously, the matrix may be rectangular depending upon the size of this, but the diagonals, the total diagonal entries are only D. The rest of the entries are all 0. So these are diagonal entries. Obviously, the diagonal entry, the diagonal matrix is defined as square, but this kind of matrix where the entries at the equal row column position, that is only on, the rest of the entries are off, this kind of matrix is called generalized diagonal if it is not a square matrix. And further, let's say this value S1 is a singular value that correspond to the vector U1. Similarly, we have, let's say have this matrix V, where these rows are written like V1 is a row, V2 is a row, and so on. So these are all the rows, and here we have, let's say, you can see how many rows do we have. Here we can have n rows. Yeah, n rows. So yeah. n rows. So by the way, if we just want to write, for example, if we want to write, let's say d is equal to, let's say 4 and n is equal to, let's say d is equal to 2 and n is equal to 4, then how can we write this matrix D? That matrix D will be some value, then 0, 0, 0, then 0, some value, then 0 and 0. And how can we write this matrix V? This matrix V will be n by n, so 4 by 4. So some value, 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 and some value, some value, some value, some value, and some value. Yeah. So this one thing to make this rectangular matrix just a square, we can pad this matrix with zeros. For example, we can pad this matrix with zeros, and things will become like more consistent. But then we have to see whether we are adding zeros to make. So here we have, for example, this d. This should stay consistent with this d, and this n, it should stay consistent with this n. So we can add, we can pad it with zeros, and we can pad it with zeros on the columns. But we have to be very, very careful to keep these dimensions, the order of matrix multiplication, consistent. So here I have just shown you an example that we have, let's say, these two values. D is 2, so these two values, and we have these matrices, these 4 vectors, because we have these 4. And let's say we have this u, where we have u is d by d. So this value, this value, this value, this value. So what I really want to mention here is a relationship, that this value corresponds to this vector and it corresponds to this vector. Now, this particular value, next one, this value, it corresponds to this vector, and here it corresponds to this vector. You might be thinking, what about these two vectors? Well, these two vectors correspond to the value 0 that we may append or may not append here. Yeah. So so if the matrix, let's say here in this case, if the matrix is 2 by 4, then what is the information in the singular value decomposition for this matrix? Well, if we just assume that we just place all the non-zero singular values in order, and the corresponding vectors in order, and all the 0 values down, then all the, even if we do not order, here is a very concrete kind of explanation of different properties of A. All the vectors in U that correspond to non-zero singular values in D, they form orthonormal basis of column space of A. Column space of A. So if you want to find out the basis of column space of A, and if you want to find out, for example, if you want to find out the orthonormal basis of column space of A, just one way is to just, if you have the SVD, then just pick the columns in U that correspond to non-zero entries in V, and non-zero entries in D. And these vectors, they actually form column space, orthonormal basis of column space of A. Not only that, the entries in V, the rows of V that correspond to non-zero singular values in D, they form orthonormal basis of row space of A. How amazing is that? You do one SVD, you have orthonormal basis of column space of A, you have orthonormal basis of row space of A in V. And the number of non-zero singular values in D, how many are these? How many singular values are non-zero? The count of that is basically equal to rank of A. So rank of any matrix is equal to the number of non-zero singular values. So now you have one matrix, you have just SVD of it, and you have a lot of information. The columns in U corresponding to non-zero singular values form the basis of column space of A. The rows of V corresponding to non-zero singular values in D form orthonormal basis of row space of A. The number of non-zero singular values is equal to the rank of A. Not only that, if we have certain columns here that correspond to zero singular values, so the columns of U that correspond to zero singular values, they form orthonormal basis of left null space of A. I know these, I have not explained this null space and row space and column space. I just want to tell you that how informative this singular value decomposition is. So the columns of U that correspond to non-zero singular values, zero singular values, they form orthonormal basis of left null space of A. And similarly, the rows of V that correspond to zero singular values in D, they form the orthonormal basis of right null space of A. And for matrix, any matrix, these are four kind of fundamental spaces that are related to matrix. Column space and its orthogonal complement, which is left null space. Both are found in U. The other space, important space, is row space and its orthogonal complement, which is the right null space. Both are found in V. And then we have one other property, the dimensions of column space and the dimensions of row space, which basically is rank of A, and that is found in D. So can you see how informative this singular value decomposition is? You do singular value decomposition of any matrix, and you have kind of post-mortem analysis of that matrix. You have bits and bytes, a lot of information about that matrix. So yeah, so that was, so in this video, we basically derive SVD and see some of the properties of SVD. In the next video, we will be actually going to Python, and we will be using this derivation that we did here. We will actually coding that. We will be building an SVD function from scratch in NumPy, and not only the implementation we will see from scratch, we will build all these things from scratch. After building those and testing those, we will be using SVD function that is there in NumPy.linear algebra library. So in the next video, I'm going to Jupyter Notebook, and we will be building some code from scratch to test the properties that we just seen for singular value decomposition. We will implement singular value decomposition from scratch, and we will see the built-in methods of SVD in NumPy. So the next video is all about Python implementation for SVD and testing certain properties. Hope to see you in the next video.